26% on the national U.S. report card. That's the percentage of 12th graders that are proficient in mathematics. In America, we pride ourselves on being nothing less than an exceptional nation. Yet, this number is not acceptable. Is it due to the fact that at least 74% of the audience is carrying a 10-digit calculator everywhere they go? Or is it because there's a lack of understanding of the beautiful, intricate complexities of mathematics? Despite popular belief, mathematics was not invented to harass English majors. It was actually invented by nature. There's a specific sequence of numbers that we see in nature quite often, which we call the Fibonacci numbers. Depending on who you ask, starts with 0 and goes 1, 1, 2, 3, 5, 8, 13, 21, and 34. This pattern was first observed in India, dating back to 200 BC, but brought to the Western world by a man of many names. Leonardo Bigola Pisano, also known as Leonardo Fibonacci, most commonly known as Leonardo Pizza, aka Fibonacci. He was a mathematician, and in his book Liber Abaci, he first described this sequence through a thought experiment with a family of incestuous bunnies. During the first season, you would have one pair of bunnies. It would take them a season to mature before producing another pair. The next seasons, the newborns would take yet another season to mature while the adult bunnies produce another pair. Each season, the number of bunnies you would have would be correlated to Fibonacci numbers, 1, 1, 2, 3, 5, and so forth. This pattern is very flawed and simply unrealistic, because it would rely on each pair of bunnies to produce twins every season, as well as, simply put, never die. This is not the easiest way to locate Fibonacci numbers in nature. Dividing any two consecutive Fibonacci numbers, especially the larger ones, will result in a number relatively close to what is now referred to as the golden ratio. The Greeks discovered this long before Fibonacci and referred to this number as phi. Phi was first reportedly used by the ancient Greek sculptor Phidias to display the ideal physical appearance in the Parthenon statue. He is said to use phi to define the proportion of the statue's total height and the distance between his toes to his waist, as well as the proportion of the face's length and the face's width. This inspired me. To create the idealized sense of perfection, there needed to be an underlying sense of mathematical patterns. At first, my project was to see if it was possible to learn music as a means of improving mathematical skills. But as time went on, I realized that this was a remarkably vague subject that has been baffling neuroscientists for years. It wasn't until my mentor introduced me to the Fibonacci sequence that I really became fascinated and intrigued by this work. My project slowly became more about the symbiotic relationship between the Fibonacci numbers and the world around us. Boethius was a clever philosopher, and similar to his Greek... I've always believed that to have something absolutely perfect, it must be incorporated with mathematics. Take nature, for example. Nature incorporates the Fibonacci sequence because that sequence of numbers provides the most efficient method to pack as many seeds into a flower or the most amount of hexagons onto a pineapple. The idea that mathematics is incorporated with nature isn't exactly new. A great philosopher once said, "Nature's great book is written in mathematics." So you see, even Galileo agrees with me. Before I continue, I'd just like to say this is going to be a lot of math. And if you don't like math or tends to put you to sleep, I'm sorry, and sweet dreams. To understand the Fibonacci sequence, you first need to be familiar with a few of its mathematical properties. Pascal's triangle is formed by adding the sums of the numbers above it. When you add all the shallow diagonals in the pyramid, you are left with the Fibonacci sequence. Another mathematical property, Cassini Catalin identities. The Cassini identities state that any three consecutive Fibonacci numbers, say 3, 5, and 8, when you multiply the outer two and square the middle, they will differ by exactly 1. 3 times 4 is 24, 3 times 8 is 24, and 5 squared is 25. Zeckendorf's theorem says that any number imaginable can be constructed by adding up Fibonacci numbers without repeating any. Say you want to make 68, 13, 21, and 34. 70 is constructed of 13, 21, 34, and 2. These are all modern-day properties of the Fibonacci sequence, but throughout time, there have been remarkably futuristic beliefs on math and music. Boethius was a clever philosopher, and similar to his Greek predecessors, he believed that arithmetic and music were intertwined, and spent his life trying to prove his remarkably modern beliefs. He classified music into three parts: Musica Instrumentalis, Musica Humana, and Musica Mundana. Musica Instrumentalis refers to the music that is played in the concert halls, made up of basic percussion instruments. Musica Humana is any sound that can be produced by the human body, whether that be clapping to a rhythm, singing, or even whistling. And the most interesting to me is Musica Mundana, which corresponds to music of the spheres. He described this as a sound planets make while they dance with one another in that atmosphere. He also believed humans were not able to hear this music, perhaps because it is too loud for us to hear. Or we've been hearing this noise since birth, we cannot distinguish it from silence. Mathematics is an art form that we use to think creatively, logically, yet we don't treat it as such. We need to shine light on the beautiful, inspirational aspect of mathematics to inspire the younger generation. My plan was simple: create a basic piece of music that was directly derived from the Fibonacci sequence, but still somewhat resembled a nursery rhyme. This part was the hardest, though, figuring out a way to overlap the two. At first, I replaced the tones in a non-tonic scale with Fibonacci numbers. I tested the first 50 tones and found no noticeable patterns. I then tried using one of the most common scales, the C major scale. The C major scale is constructed of 7 tones: C, D, E, F, G, A, and B. I inputted my formula by corresponding Fibonacci numbers with tones on the scale. 1 would equal to C, 2 becomes D, 3 would equal to E, and 5 would be the 5th note on the scale, G. There's no 6 or 7, so I go directly to 8. What I'm doing here is counting up 7 tones on the scale and assigning a Fibonacci numbers to each. When I reach the end of my scale, I repeat. I inputted the first 32 Fibonacci numbers with my scale and was left with this. The pattern created a 16-tone scale that infinitely repeated itself. I then got to work on creating a rhythm. I still want to incorporate the Fibonacci numbers, so I made each octave a Fibonacci number. If I replace the first octave with the rest, my scale fits perfectly with the rhythm. The only problem was that it had a very robotic sound. It was a very plain and boring piece of music that I wasn't proud of. So I got back to work, experimenting and trying things I wasn't familiar with. My mentor recommended that I try using a musical software application to make a more professional-sounding piece. But I had the same problem. I didn't enjoy the final product. I finally decided to change the rhythm to something that didn't involve the Fibonacci sequence, but still sounded good. I didn't want to add any additional beats or chords or sounds. That way the Fibonacci numbers could be the star of the show. So as not to waste too much time, here's the chorus of the melody with its counterpart in guitar tab. As a student that is fascinated with mathematics, I enjoy solving equations. I enjoy the sense of accomplishment you get after you solve a long, challenging, lingering problem. That's why I bring up this number again. 26% remains as the percentage of 12th graders proficient in mathematics. I challenge you to help raise that percentage, even if you aren't a 12th grader or living in America. We need to teach mathematics in a way that inspires and motivates others. Just to show on the list of endless gratitude, I'd like to thank Ibu Jackie for helping me throughout the Quest project. To Pac Alex, without him, I couldn't imagine creating my melody. To the friends and teachers who have always been supportive, and most importantly to my family, who has been nothing but helpful. I'd like to leave you off with the wise words of Arthur Benjamin. Mathematics is not just solving for X. It's also figuring out why. Thank you.